Hello everyone, welcome back to our channel. In the previous video, we learned about the half adder and how it adds two single-bit binary numbers. In today's video, we are going one step further and understanding the full adder, an essential combinational circuit that forms the core of multi-bit binary addition. A full adder expands on the idea of a half adder by adding three inputs instead of two, and producing both sum and carry out. So let's get started and explore how the full adder works, why we need it, and how it helps build advanced arithmetic circuits. Now let's understand what a full adder is. A full adder is a combinational logic circuit that adds three input bits A, B, and a carry-in from the previous stage. It gives two outputs, the sum and the carry-out. This circuit is extremely important because it is used to build multi-bit adders inside processors and arithmetic units. Before we begin the full adder, let's understand why we actually need it. In the previous video, we learned the half adder, which can add only two single-bit inputs, but when we add multi-bit binary numbers, there is always a carry coming from the previous stage. A half adder cannot accept this carry input, so it cannot perform multi-bit addition. To solve this problem, we use a full adder. A full adder adds three inputs, A, B, and the carry-in. This makes it possible to perform bit-by-bit addition inside processors, ALUs, and ripple carry adders. So, the full adder is simply an upgraded version of the half adder that can handle the carry-in. Before we start building the full adder, let's quickly refresh the rules of binary addition. When we add two bits, the results are simple: 0 plus 0 gives 0. 0 plus 1 gives 1. 1 plus 0 also gives 1. But when both bits are 1, the result becomes 1 0 in binary, where 0 is the sum, and 1 becomes the carry. Now, in multi-bit addition, we also have a carry coming from the previous stage, so along with A and B, we need to add one more input called carry-in. This is exactly why a full adder has three inputs and not just two. Now let's look at the truth table of a full adder. A full adder has three inputs, A, B, and carry-in. The sum becomes 1 when an odd number of inputs are 1, the carry-out becomes 1 when at least two inputs are 1. This table shows all 8 possible input combinations and their corresponding outputs. Now let's move on to the next slide, which explains the K-map simplification for the sum output of the full adder. The sum expression of a full adder depends on three input variables, A, B, and carry-in. From the truth table, the sum becomes 1 in 4 specific cases, and we place these ones inside a 3-variable K-map. After filling the K-map, we form valid groups of adjacent ones. When we simplify these groups, we get the sets of expressions, which finally reduce to a single clean output. The simplified Boolean expression we obtain is A, XOR B, XOR carry-in. So, the sum output of a full adder is simply the XOR of all three inputs. Now let's simplify the expression for the carry output using a 3-variable K-map. Carry, which we denote as Cout, becomes 1 whenever any two or more inputs among A, B, and Cin are 1. From the truth table, the carry output is 1 for the minterms M3, M5, M6, and M7. With the K-map filled, we identify the best possible groups. The cells M6 and M7 form the first group, giving the term A, B. The cells M5 and M7 form the second group, giving the term A, Cin. And finally, the cells M3 and M7 form the third group, giving the term B, Cin. Combining all these terms, the simplified expression for the carry output becomes Cout equals AB plus ACN plus BCN. This is the final minimized carry expression for the full adder. Now let's look at the logic circuit of the full adder. This circuit uses one XOR gate, three AND gates, and one OR gate to generate the sum and carry outputs. First, observe the XOR gate at the top. It takes all three inputs, B, and the carry-in, and produces the sum output. Next, we have three AND gates. Each AND gate handles a different pair of inputs, A and B, A and Cin, and B and Cin. These three partial carry terms are then combined. Finally, all three AND gate outputs are passed into a single OR gate, which produces the final carry out of the full adder. So together, the XOR gate generates the sum, and the combination of AND OR gates generates the carry output. Now let's build the full adder using two half adders. In the first half adder, Inputs A and B are applied to the XOR gate, this generates the first intermediate sum, and the AND gate produces the first carry. The intermediate sum from the first half adder is then given to the second XOR gate along with the Cin, this produces the final sum output of the full adder. At the same time, the carry from the first half adder and the carry generated by the second AND gate are combined using an OR gate. The OR gate output becomes the final carry out, so, using 2 XOR gates, 2 AND gates, and 1 OR gate, we successfully construct a full adder using 2 half adder blocks. And that brings us to the end of the full adder concept. We started from the basics, understood the logic, explored the K-map simplifications, and finally built the complete full adder circuit. If you found this video helpful, make sure to like, share, and subscribe to our channel for more digital electronics content. If you have any doubts or suggestions, feel free to use the comment section. Thank you.